When designing fire sprinkler systems, whether using standard spray, extended coverage, residential, or CMDA sprinklers, we encounter a key concept: density. In this video, we'll explore what density means in the context of hydraulic calculations and why it plays a critical role in determining system performance and compliance. When we hear the term density, we often think of its definition in physics, mass per unit volume. But in fire sprinkler system design, density refers to something entirely different: the flow rate per unit area. In imperial units, it's measured in gallons per minute per square foot. In metric, the unit is millimeters per minute, which might seem unusual at first glance. In metric units, liters per minute per square meter might seem more familiar and intuitive. But let's break it down. A liter is equal to 0.001 cubic meters. Now, if we divide cubic meters by square meters, we're left with a unit of meters. Specifically, that's 1 millimeter. So when we express sprinkler density in millimeters per minute, it's simply another way of saying how deep the water layer would be if evenly distributed over the area. Based on the definition of density, we understand that increasing the flow rate per unit area enhances the potential for controlling or suppressing a fire. This leads to a critical design question: how much density is appropriate for a specific hazard? To answer that, extensive fire testing has been conducted, and the results are compiled in NFPA 13 through its tables, figures, and design criteria. These resources help designers select the correct density based on occupancy type, hazard classification, and system configuration, ensuring both performance and compliance. One of the most fundamental applications of density in sprinkler system design is answering a critical question: what is the minimum acceptable flow rate for a sprinkler? To find the answer, we simply multiply the required design density, as specified in NFPA 13, by the coverage area of the sprinkler. For example, in an ordinary hazard group 2 occupancy, NFPA 13 requires a density of 0.2 gallons per minute per square foot. If a sprinkler covers 100 square feet, the discharge flow rate must be 20 gallons per minute. This ensures that each sprinkler delivers the minimum amount of water needed to meet the hydraulic demand for effective fire control. The next point we'll explore is the effect of density on sprinkler system layout. In extra hazard occupancies and high piled storage applications, the coverage area and spacing of standard pendant and upright spray sprinklers are directly influenced by the required density. When the design density is equal to or greater than 0.25 gallons per minute per square foot, the maximum coverage area per sprinkler is limited to 100 square feet, with a maximum spacing of 12 feet. However, if the required density is less than 0.25 gallons per minute per square foot, the allowable coverage area increases to 130 square feet, and the spacing can extend up to 15 feet. This adjustment reflects how higher densities demand tighter control over water distribution, while lower densities permit broader coverage, ultimately shaping the physical layout of the system. Although the equation Q equals K times the square root of P shows that we can achieve higher flow rates by increasing the pressure, this approach has limitations, especially in high challenge storage fires. In these scenarios, it's not just the flow rate that matters, but also the size and momentum of the water droplets. As pressure increases, the droplet size decreases, which in turn reduces their momentum, calculated as mass times velocity. Droplets with lower momentum may fail to penetrate the fire plume, which has its own upward momentum, Without sufficient impact, these droplets cannot reach the burning surfaces effectively, and the sprinkler system may struggle to control the fire. Therefore, to help manage operating pressure and ultimately control droplet size and momentum, NFPA 13 specifies requirements for control mode density area or CMDA sprinklers. In storage applications where CMDA sprinklers are used, the required density directly influences the minimum K factor of the sprinkler. As outlined in Chapter 21 of NFPA 13, the minimum K factor varies based on the design density. For densities up to 0.2 gallons per minute per square foot, the minimum K factor is 5.6. For densities greater than 0.2 and up to 0.34, the minimum K factor increases to 8.0. And for densities above 0.34, the minimum required K factor is 11.2. To review the topics we've covered in this section, let's walk through a practical example. Suppose NFPA 13 requires a design density of 0.4 gallons per minute per square foot for a specific commodity and configuration using CMDA sprinklers. If each sprinkler covers 100 square feet, the required flow rate would be 40 gallons per minute. Now, regardless of the K factor requirement, if we were to use a K 5.6 sprinkler, the pressure needed to achieve 40 gallons per minute would be approximately 51 pounds per square inch. However, NFPA 13 specifies a minimum K factor of 11.2 for this density range. With a K 11.2 sprinkler, the required pressure drops significantly to just 12.7 psi. As we've discussed, lower operating pressure helps produce larger droplets with greater momentum, improving their ability to penetrate the fire plume and enhancing overall fire control effectiveness. In Chapter 19 of the 2025 edition of NFPA 13, new requirements were introduced that link design density to ceiling height in certain occupancies. Specifically, in ordinary hazard group 2 and extra hazard occupancies, the minimum required density increases as ceiling height rises. For example, in OH2, when the ceiling height is more than 30 and up to 40 feet, the minimum density shall be 0.37 gallons per minute per square foot. If the ceiling height exceeds 40 feet, the minimum density increases to 0.45. Similarly, for extra hazard occupancies, a minimum density of 0.45 gallons per minute per square foot is required when the ceiling height is greater than 30 feet. These updates reflect the increased challenge of controlling fires in taller spaces, where sprinkler activation may be delayed, allowing the fire to grow larger before effective fire control begins. As we explained at the beginning of this video, larger fires require higher design densities to achieve effective control. This principle allows us to use density values as a practical tool for comparing the relative fire severity of different materials and configurations. For example, if we want to determine which type of Group A plastic, expanded or unexpanded, cartoned or exposed, stable or unstable, creates a more severe fire hazard when stored palletized, we can simply refer to the decision tree and related tables in Chapter 21 of NFPA 13. Based on this evaluation, expanded, exposed, stable plastics represent a higher hazard classification, as they require a greater design density for effective fire control.